All right, well, welcome to the penultimate week of vector calculus. We got 2 weeks to go and we're cruising right along. We're doing great. We only have 3 sections left to cover, so we're like perfect with time. And so our plan today is actually to introduce you to parametric surfaces and surface integrals. So you know about how to parameterize curves and do line integrals. Well, this is really the same idea, just with surfaces in space instead of curves. So that's where we're heading today. You're going to see a lot of similarities, a lot of things that we can tie back to from before. But anyway, so that's where we're heading. But before we do that, as always, let me offer up any questions on homework or anything else we've talked about.
Yeah, can we go over problem 6 in homework 6.4?
All right, 6.4, number 6. Got that on my list. Anything else? All right, well, then let's go ahead and start with that and see where it takes us. If other stuff pops up, just let me know and we'll take a look. So I'll go ahead and share my screen and we'll take a look at that guy. All right, so 6.4, number 6. So just looking and seeing what's doing here, we got Green's theorem and divergence and curl. So obviously it's a question about Green's theorem. How do you guys feel about divergence and curl? Feeling pretty good about that stuff?
Yeah.
Hopefully you see it's like, it's really procedural finding it. It's not that big of a deal. All right, well, that's cool for me. All right, so let's go take a look at number 6. All right, so it says C is a circle with radius 5, centered at the point 4, -5. We want to evaluate this integral. And notice that they've got the pi outside the box. So when we get an answer, if it's a multiple of pi, we're going to put the multiple into the box. So let's think about our options here. So one option is to parameterize the curve. We know how to parameterize circles really easily, right? The x would be 5 cosine theta. The y would be 5 sine theta, except for the fact that we're centered at the point 4, -5. So that would actually require us to fiddle around with it a little bit. It's not that much worse. It's just a matter of adding and subtracting those coordinates from the center to shift. So we could do that. And then once we've got those, we can plug them into the function and then take their derivatives to get the dx's and dy's, get it all in terms of t, and then do an integral from 0 to 2 pi. So that's an option. However, it's not the option I'm going to use. And it shouldn't be the option that you want to use either. Because that's going to be pretty gnarly. I mean, look at that function and think about replacing everything with those parameters, right? Like look at that first part, we're going to have e to the sine of x. So that's going to be e to the sine of the cosine of stuff. I don't want to do that. You shouldn't want to do that. So instead, let's use Green's theorem. And, or at least try Green's theorem. Because we know that we could use it here since we have a closed curve, right? It's a circle of radius 5. All right, so let's go to whiteboard. Actually, let me write these down real quick and then. get the pertinent information. All right, so let me share a whiteboard screen. All right, so for this one, our vector field is going to be this. It's going to be 5y minus e to the sine x, comma, 11x minus sine of y cubed plus y. And I got that by looking at the integral when it's in that differential form with the something times dx plus the something times dy. The multiplier on dx, that's our p, according to this book. And then the q is the part that's attached to the dy. All right, so for Green's theorem, we're going to want to look at qx and we're going to want to look at py. So qx, the derivative of the second one with respect to x, is 11. And py, it's the derivative of the first one with respect to y is 5. And I would have wanted to do this anyway, even if I wasn't thinking Green's theorem, because if those were equal, I'd be done. Because what would the answer be if these were equal?
0.
Yeah,
0.
It'd be 0 because it's a conservative field. Everything's great. Okay, it's not conservative, but I can still, if I'm going to use Green's theorem, put those guys in here. So I'll get my 11 minus 5 dA. So really, I'm just looking at the double integral of 6 dA. And this region, we were told that we were centered at 4 minus 5 and had a radius of 5. So there's our region R. So at this point, we can set up our double integral, doing whatever our favorite method is, or we can be smart, remembering that if you have a constant, if you pull that out, the double integral of dA is just the area of the region. So I'm not even going to bother doing an integral. I'm just going to calculate the area of this region. And since it's a circle, I know its area, right? It's pi r squared. Well, they told me that the radius was 5. So that's going to be 25 pi. So that means that my total integral is 6 times 25 pi, or, oops, not 125. How about 150 pi? Excuse me. So if you integrate this field over that entire curve, you're going to get 150 pi.
Wow, that helps a lot. I was really confused and tried to apply polar transformation in order to solve the double integral, and that was very messy because the center point wasn't the origin. So
yeah, if you wanted to set this up as a double integral, right? Like you could get the equation of this. It's x. I think I remember what the points were, but I think it's this guy, right? X minus 4 squared plus y plus 5 squared equals 25. And so if we are going to try to do this, like you could do it in rectangular, solve it for y, get your plus or minus square root business for top and bottom, and then your x's are going to go from 0 to, or no, -1 to 9, I think, right? Or solve for x's and have your y's go from -5 to 0 or -10 to 0. But then, yeah, trying to do this in polar is a little bit wonky because you're not centered at the origin. And so what you really want to do is a UV transformation where you'd say, okay, let's let u equal 5 cosine of theta plus 4. And then let v equal 5 sine theta minus 5. So the 5 cosine and the 5 sine should make sense because it's radius 5 circle. And then the +4 and the -5, just make it so that when you plug those things in, they cancel that shift, right? That deals with the transformation. And you could then do the Jacobian on that, you know, do the whole thing. I guess actually we should let that be R cosine and R sine, because we're going to go from 0 to 5. But anyway, that's the kind of trick you would want to play if you were going to try to do this as a double integral. And it's the kind of trick that you would have to play if this hadn't been nice. Like the fact that this ended up just being 6 let us do the shortcut. Otherwise, it would have had to have been a play kind of like that. So, Jacob, I'm not sure exactly how you set yours up, but this is what I would do with my transformations. So, anyway, better for that one?
Yes, much better.
Okay.
Definitely.
So just watch for this trick. Watch for this guy. Whenever this is a constant, just keep this in mind, because sometimes finding the area is really fast and really easy. Like in this case, it was really clear what it was. And if it's not really clear, then you probably are going to have to set up a double integral anyway to try to calculate the area. And if you're going to have to do that, you might as well just, you know, do it here. All right, so good for that one.
Definitely.
All right, anything else from the homework that we want to look at before we dive into new stuff? All right, hearing none makes me think we should be good to go. So I will jump over to the whiteboard. I will see you guys in just 1 second. All right, so now we're ready to start looking at surface integrals. Now, the idea of a surface integral is exactly the same as a line integral, except now adding up a function over some path, we're going to add up a function all along a surface. All right, so now maybe we've got like a sphere, and we want to add up the total charge on the outside of the sphere. So if we knew how charge was distributed in space, so we've got a function for charge, we could integrate that function over that surface. So we're not talking about what's inside the surface. That would be a triple integral, right? If it's a closed surface. We're not looking at any kind of a cross section on it or anything. It's just on this surface, what's our total for this function? Okay, so that's our goal. But to do that, we need to investigate surfaces a little bit, because go back to line integrals. Remember, with line integrals, all we were doing, integrating over some sort of a curve of an f ds, right? So we took our, actually, let's not call that big F, because it wasn't necessarily a field. It was just a function. So f of, and I'll put here x, y, z, because it could have been a 3-dimensional curve, right? Cruising through space. But we just took our function and multiplied it by a little differential chunk of length. Okay, so now let's think about if we're going to do this on a surface. For a surface integral, it should come as no surprise that we're going to have to do a double integral. Does that make sense? Can you see why we'd have to do a double integral?
Because we're looking for a dA.
Yeah, it's going to be now, if we're talking about a surface, the little chunks of our surface are little area chunks on our surface. So we're still going to have good old f, x, y, z, but now this is going to be a dA. And what we're going to do is, I'm going to use the letter S to represent a surface. Actually, just made me wonder what the book does. Hey, they use an S as well. Awesome. Okay, so this is now going to be, we're integrating the function. We're taking our function value times some little differential area on our surface. Okay, well, that should make sense. We're finding a surface integral that has to do with surface areas. So it has to be a little dA. Okay, now go back to the line integral. This form, like the definition form, was pretty useless, right? I mean, honestly. So what did we do? What did we do like every time we had a line integral to actually integrate?
We parameterized it.
Yeah, we had to parameterize that curve. We had to turn it into something that wasn't the arc length parameter because that was a little bit difficult and kind of bulky. Well, the same kind of deal is going to happen here because the surface area parameter, yeah, and no, it's not going to work out for us. So we're going to do exactly the same thing that we did before, which is we're going to parameterize the surface. So let me just go ahead and put this here. We need to parameterize. Okay, now this is something you've probably never done before. If you came through our sequence, you don't see this up to this point, but potentially you took math classes elsewhere, and so you might have seen it, but most likely you haven't. So here's the deal. When we parameterize a surface, we're actually going to need two parameters, not just one. One parameter is perfect for a curve, but for a surface, we're going to need two. And again, this should kind of make sense because a surface is two-dimensional. So since it's a 2D surface, we're going to need two parameters. But it's the same kind of idea as what we did before. We're just going to describe the surface using these two variables. Now, in general, the parameters we use are u and v. They don't have to be u and v. I mean, anything else. They can be theta and phi. They can be r and q. They can be, whatever. But we tend to just use u and v, kind of like when we do one parameter, we use t. But even there, we don't always use t. Sometimes we use theta or whatever else. Well, same kind of deal. But we're going to tend to use u and v. Now, these are not vectors. These are just regular old scalar numbers, u and v. But they're going to vary, and they're going to help us determine our surface. All right, so for example, here is a parametric surface, and let's talk about what it looks like. All right, so this surface, we can think of it this way. I'm going to say that x is going to be given by u, or no, not u. How about just 4 cosine u. Y is going to be 4 sine u. And z is going to equal v. Okay, so the way that this plays out is we're going to get a whole series of points that are going to come from letting our u's and our v's be whatever values we want. We can also restrict them. I mean, you saw that with parameterization of curves. We could say, okay, well, we're going to take this thing, but only t's between 0 and 4 or something like that. We could do the same thing here. But I'm going to let u and v be whatever we want. Okay, so let's think about what this is going to look like. First of all, what kind of numbers are we going to get out of x? What are the possible values there?
Between 0 and 4.
All right, not quite. You're right that the max is 4. There you go. Victor just threw in the chat box.
All right, the minimum is -1. No,
Negative 4 and 4. Yep. Okay. So the x's are going to go between -4 and 4. And we're going to get all those numbers between -4 and 4 at some point. What about the y's? Well, the same, right? They're just out of phase. And then what about the z's?
-infinity to +infinity.
Yeah, we're going to get all real numbers, so it can actually take on any value we want. Okay, but take a look at x and y, because when I wrote x and y, I'm going to guess that most of you thought something. What did you think when you saw those x and y?
Polar coordinates.
Okay, good. So you started thinking this is like polar, which hopefully made you start thinking circles. Because the x and the y together, these are going to form a circle. They're going to give us a circle of radius 4. So even if we don't worry about the v, let's not take the v into account just yet. If you ignore that, then what you see is the x's and y's are just giving us a circle. So no matter what v is, the u's are going to give us circles. All right, so in the x and y plane, we're going to see circles. And then what happens if we start changing v? Well, we're going to get that same circle just located somewhere else. So Victor's right. This is exactly what we're getting here is a cylinder. All right, this surface right here, this is a cylinder. And it's a cylinder like you think of as a cylinder. And so the V's are letting us go up and down wherever we want to be. And the U's are drawing circles at every one of those V's. So this, for example, is a parameterization of a cylinder. All right, so this is kind of how they play out. Just like before, except we have to keep track of 2 parameters and see what's happening with them. Now, this one was kind of nice because the one parameter didn't affect the other, right? I mean, they were like the V only came into play with the Z coordinate, and the U's only came into play with X's and Y's. There wasn't a lot of crossover. But this is the general idea of parameterization. Okay, now I told you that you haven't seen this before, probably, except you have. You absolutely have seen parameterization when it comes to surfaces. In fact, you've seen this, kinda. Where have you seen this sort of set of translations between X, Y's, and Z's and something else? That maybe
Spherical.
Cartesian and cylindrical.
Yeah, this is cylindrical. Think about the conversion to cylindrical. It's X equals R cosine theta, Y equals R sine theta, and Z equals Z. Well, this is a parameterization there where we fixed our radius. So you could do the same thing for a sphere. Check this out. Suppose we want to parameterize a sphere that's centered at the origin with radius 10. Okay, so we want a sphere centered at the origin with radius 10. Okay, so here's what we're going to do. Let's go to spherical. Let's go to spherical conversions. So the spherical coordinate conversions, it was rho cosine theta sine phi. Y was rho sine theta sine phi. And Z was rho cosine phi. But now here, I've got my radius is 10, which means that's what I'm going to put in for my rows. And so if I want to parameterize this, and we'll use again U and V, here's what I'm going to do. I'm going to let my X equal 10 cosine U sine of V. Y is going to be 10 sine of U sine of V. And Z is going to equal 10 cosine of V. And so there's the parameterization for a sphere of radius 10 that's centered at the origin. So I kind of lied when I said you've never seen this before. I mean, you have-ish. You've kind of seen where we need more than one quantity to describe these surfaces in space. And cylindrical and spherical coordinates actually are a really good example of places where if all we do only changes, we specify a radius for either one of them. So either the R for the first example or the rho for the second, and we get these guys. I'll continue to show you more ways of parameterizing, but just wanted to lead with a couple of examples that you know. All right, so yay-ish. Now, what we are going to do is instead of representing them as lists of X, Y, Z, we're going to actually put these together as a vector valued function. So what I'm going to do is I'm going to describe this surface, instead of writing it like this, I'm going to write it as R of UV. So for this one, it would be 10 cosine U sine V, comma, 10 sine U sine V, comma, 10 cosine V. Now, the fact that I'm using a vector valued function to describe this should not bother you whatsoever, because we've done that before. You think of surfaces as R of XY, right? So think about these vectors. Again, they're pointing from the origin to the point that's on the surface. And so we're just keeping track of where the end of that point is, or end of that arrow is. And if you collect all those endpoints, it forms the surface. Okay, so this is going to be pretty standard. We're going to go ahead and just do it like this and think of it as a collection of vectors. It's really the tips of the vectors that form our surface. All right, so, yay. But you can imagine that parameterization can get a little bit tricky depending upon what the surfaces look like. And that's definitely true. But what I want to do is I want to give you a couple of ways that you can describe surfaces parametrically with some specific forms, specific types of surfaces that come up. Right? Obviously, cylinders and spheres, well, cool, we've got cylindrical and spherical, but how often are we dealing with spheres? And how often are we dealing with cylinders? Not that often, right? I mean, because what if we have a cone, or heaven forbid, a hyperbolic paraboloid, Whoa, right? What happens when a Pringle shows up? Or what if it's something even funkier? Well, let me give you some ways that you can represent some of this stuff easily with parametric curves. And please jump in if there's ever a question about what I'm doing here. All right, so let's talk about functions. Like, how can we parameterize functions? Okay, so these are the type that are z equals f of x, y. All right, so this is anything that you can write as z equals. So a plane, a lot of the quadric surfaces, right? Like elliptic paraboloids or, whatever. We just have to write z equals. All right, if you ever are trying to parameterize one of those, these are easy, 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 easy. Here's what you do. You let x equal u and y equal v. And then your z is going to be whatever the formula is, just replace u and v. This is exactly analogous to when you let x equal t for a curve. You remember those, right? Like if we had the function y equals x squared, you go, okay, well, x equals t, and then y equals t squared. Well, that's exactly the same idea here. All right, so what this is going to look like, if we do our parameterization, r of uv is going to equal u comma v comma f of uv. So these are the ones that are going to feel cheap. You're going to feel like you're not really doing anything, and yet you are parameterizing the surface. Just like with the ones with curves, it always probably felt like you weren't really doing anything by letting x equal t, but it got it into the form that we could then use. Okay, so for functions, nice and fast, nice and easy, right? So for example, let's just do a plane real quick. What if we had the plane that was given by 3x minus 2y plus z equals 4? So what we want is z equals, so if we just change this real quick, we get z is equal to 4 minus 3x plus 2y. So its parameterization then is going to be u comma v comma 4 minus 3u plus 2v. And there you go. You just parameterized that plane. Piece of cake. All right, so how are we feeling about those? Thumbs up?
Yeah, it does kind of seem like cheating almost.
I know. And this is also one of those times when you're like, but math's supposed to be hard. Well, not always. Right? So when we've already got a function, we're done. All right, the other big set of surfaces that are pretty easy to deal with are surfaces of revolution. All right, so surface of revolution, you know what I'm talking about. We've got some sort of a curve that we're then rotating about an axis, right? So let's just say we're in this is the XY plane, let's say. We've got some sort of a curve that we then revolve around, say, the x-axis. And this is giving us like a little trumpet kind of shape, the one that I've drawn right here. But this would be a surface of revolution. All right, so you kind of remember these, I hope. You did a lot of this stuff back last year when you were doing applications of integrals, finding volumes and surface areas and whatnot. But let's talk about parameterizing these. Okay, now, we're actually going to do kind of similar thing to what you did when you tried to find areas and whatnot. And that is by looking at the cross sections. Like this one, the cross sections are always circles, right? They're always going to be circles of some type. The size of the circle is going to change. The radius changes depending upon the function value. But the cross sections are still all circles. Okay, well, let's say that this guy is y equals f of x. Well, that's actually also the radius of that circle. Now that circle is going to be in the YZ plane. Right, that circle would be in the plane that's perpendicular to the whiteboard, so it'd be the YZ plane. So that tells me that for y and z, I need to do good old r cosine theta and r sine theta. Doesn't matter which one's cosine, which one's sine. But the r's are actually going to be determined by that f of x. Now, the x's are just going to be whatever our x happens to be. So in terms of the x, no, x is equal to x. All right, so we got to get our two parameters now. Well, one of the parameters is going to be the x. We can let that equal u. So what I'm going to do here for my r of uv is I'm just going to let x equal u. So then for y and z, obviously x is one of the parameters, so that's going to be u. So what's the v going to be?
Theta.
Yeah, the only other one out there, which is theta. So we're going to get u, f of u cosine v, comma, f of u sine v. And so there's a parameterization for the surface of revolution. And it totally doesn't matter what this is. It could be y equals x. So it's just a line. It could be y equals sine of x. Okay, well then that's what we're rotating. Whatever we happen to be rotating, this is what we're going to get. But notice, again, that this was specific to revolving about the x-axis. Right? I rotated this sucker about the x-axis, and that's how this parameterization played out. Okay, well, let's make it so that we're rotating it about the y-axis. So instead of this picture, let's rotate it about the y-axis. So we're getting this bowl instead. All right, so now, again, cross sections are circles, but in which plane do these circles lie? The green ones, what plane is that?
The ZX plane.
Yeah, that's the ZX plane. So that means that our X and our Z are going to be giving us the circle. All right, so I'm just going to change this instead of X, Y, and Z how I had it before. We'll let X and Z be R cosine theta and R sine theta, and then of course Y is just going to be Y. Now, the radius isn't given by the y anymore, right? The radius is now given by the x. But x is now a function of y. So in this kind of example now, we'd say, okay, so instead of before it being y equals x squared, now it's going to be x equals square root of y, right? You're used to doing that when we integrate sideways instead of vertically. It's the same idea. All right, so if we go about the y-axis, notice what happens. Now we're going to have the x is going to be f of u cosine v. The y is u. And the z is still an f of u sine v. Just realize that these f's, in the first one it was f of x, now this is f of y. All right, well, we have one more axis to do. It would be about the z-axis, but I think you can see what's going to happen. Now the z is going to be our u, because the z is allowed to change freely. And then the x's and the y's are going to form our circle because we have cross sections that are circular, and those cross sections are in the xy plane. Right. So I'm going to go ahead and put that just to be complete here. But now we'd have f of u cosine v, comma, f of u sine of v, comma, u. And so this is one about the z-axis. And actually, go back and look at the cylinder, the very first one I showed you. In terms of its parameterization, I forget what the radius was, so I'm going to call it 5 because I don't remember. But you saw that it was 5 cosine, oh no, it was 4. 4 cosine v, 4 sine v, u. Well, isn't that exactly what we just did? We took the function z equals 4 and, or not z equals 4, sorry, the function 4, and we rotated it because 4 was just that line. You take that line and you rotate it about an axis and you get a cylinder. Or go and look at your spherical. Actually, the spherical is a little bit harder to see because we don't have just plain old U. Ignore that, forget about cylindrical or spherical. But spherical, you could actually describe it the same way. It's just going to be a little bit more complicated because it's going to have square roots and all that. The spherical conversion for the points already takes that into account. But you can do this for anything that's rotated about an axis. All right, so there are a couple more parameterizations that are just a little bit more straightforward, a little bit easier to use. So watch for them. Either surfaces of revolution, or if you've got a function, those two are also really fast. All right, so parameterization. Now that we've got that, we should probably look at those integrals and see how do we change those integrals in terms of that these now u's and v's. So that's going to be our next step here. All right. So think about what we did before. When we took a line integral and we parameterized in terms of t. We had to do a couple of things. One, we had to change our function. Well, that's a no-brainer, right? You just replace x, y, and z with whatever your parameterization is, and you're done. So that's a trivial step. But the other step that was really important was the replacing that dA. All right. So what does that mean? What are we going to have to do here to replace that dA?
Find a Jacobian.
Yeah, it's going to be, we're going to have to find a Jacobian, right? We think of that dA as a, you know, a dx dy or something like that, but it's not exactly dx dy because we're not in the plane. But we need the Jacobian. We need the Jacobian over this guy. All right, so how do you find the Jacobian? So Victor put on there, find dx du, dy dv. All right, yeah, we're going to want to do exactly that. But remember what we're going to need, since this is three-dimensional, since our parameterization is, we've got x, y, and z in terms of u and v. We're going to have to bump this up just a notch, right? Not only do we need a du dx, but we need a du dy, but we're going to need a du dz, right? And the same thing with the v's, although really what we need is dx du, dy du, dz du, right? But we know that we can do it the other way and just flip it over. Okay, so how did we actually find that? Do you remember how we found the Jacobian once we had all those partials?
Took the determinant of the matrix.
Okay, so we took the determinant of the matrix, so we're going to have to do a determinant of the matrix kind of thing again. All right. But now this is where it gets a little bit weird again, because we've got 3 dimensions, but we've only got 2 parameters.
Well, it's going to become vector, so ijk.
Okay, so it's going to be the good old IJK business. All right. So let's just start thinking about what this is going to look like to find that Jacobian. We're going to need a dx du, dx dv, or actually, oh no, let's do it this way: dx du, dy du, and a dz du. We're going to need a dx dv, dy dv, dz dv. But again, to make it 3-dimensional, we need a ijk. Starting to look familiar.
Isn't that the curl?
Is that the
Like
curl?
curl of a field?
Not quite, but pretty darn close. But it is a cross product. It's definitely a cross product. What is this row? Think about what we're doing is we're taking the derivative of the first piece with respect to u, then the second piece with respect to u, and then the third piece with respect to u. Well, it's not quite the gradient, but it's just the derivative of r with respect to u. This row right here is ru. The other row is rv. So what we're really doing is we're crossing RU and RV. We're crossing the two partials. Okay, now that doesn't actually give us our Jacobian though. Why isn't that enough? What's the problem with trying to make a Jacobian out of RU cross RV?
Don't you have to do 1 over?
So I'd have to do the 1 over if these were du dx, du dy, du dz. So I don't have to do the 1 over, but I'm glad you were thinking there. That turns out that's not the thing we have to worry about. Okay, there it is. So Victor just said in the chat box, the Jacobian is not a vector. And RU cross RV is a vector. So what we really need is a scalar that comes from this vector. How do you get a scalar from a vector?
You dot it.
Dot product.
Okay, so you can dot it with another vector. Cool, that's one way. I don't want to do that. I don't want to introduce another vector. What's a pretty important scalar that's part of any vector? Like if I give you a vector, what scalar is in here that matters the most?
Big T? No, it's a vector too.
Gradient?
No. Yeah, big T is a vector, gradient's a vector, big N's a vector. You're way overthinking it. How about its magnitude?
Oh, duh. Yeah.
Like I said, you're just overthinking it. Right? So it turns out that the Jacobian is the magnitude of RU cross RV. So you can actually see this geometrically. The RU and the RV, if you were to take this surface and kind of break it up into pieces, it would look like a quilt that has little parallelograms that are all connected. Those parallelograms, the two sides of the parallelogram, are RU and RV. When you cross them and take the magnitude, you actually find the area of that parallelogram. So geometrically, it follows the same thing. I just like using the Jacobian argument because why not? All right, so long story short, very long story, shortened very much so. It turns out that for a surface integral, what we're going to do is have the double integral of our function, but now in terms of u and v. And we're going to use whatever our parameterization is. So hopefully you guys are cool with that. Like technically it's every x gets replaced with the x component, the y gets replaced with the y component, and so on. But I just want to make it so it's easier to write. It's just going to be f of uv and then it's going to be multiplied by the magnitude of RU cross RV. And I'm going to go ahead and write dA again, but I want to make sure you understand that this dA, well, no, let's just do this. It's either going to be du dv or dv du, whichever way we decide we want to do it. All right, so let me show you how we do this. And we're going to start with actually a simple thing that we want to do. I just want to find the surface area of a surface. Okay, that's all I'm going to do. I'm just going to find the surface area of a surface. So if I'm going to find the surface area using a surface integral, what function am I going to integrate to get surface area?
A constant, or 1.
Yeah, I'm just going to integrate 1. All right. So this is like the easiest thing to do with surface integrals. And that's to find surface area. So the surface area is just going to be the double integral of 1 du dv. Right? Because it would just be the surface integral of 1 dA. But then when we use the Jacobian, it becomes this. All right, so let's do this. Let's find the surface area of this surface. We're going to let RUV equal U cosine V, comma, U sine V, comma, U. And let me give you some restrictions on the U. And on the V. So before we go and we find that surface, the surface area, I want you to see if you can figure out what that shape looks like. So what does this shape look like? All right, so Ralph just threw out circle. So remember, it's a surface. It's actually a surface in space, so it's not just a circle. Unless you mean a disk, but it's not going to be quite a disk. All right, so Victor just said cylinder. Closer. It's not actually cylinder. But the fact that you guys are seeing like circle, cylinder makes sense, because if you just look at the X and the Y, we definitely have circular cross sections. All right, so helix. Helix is a curve, not a surface. Oh, we're so close. Think about this circle for a second. What's the radius of this circle?
U.
Okay, it's U, which means it's not constant. It is changing. And if you think about where we are, we're going from 0 to 4. So the circle starts with a radius of 0 and goes out to a circle of radius 4.
A cone?
Yeah, there it is. All right, and Jesus just typed that into the chat box too. Yeah, this is actually a cone. If you think about it, the radius of the circle is changing with the height. So as we're going higher up, our radius is getting bigger. And so what this looks like is that. Or think about it this way. This was a surface of revolution. Remember the cosine B sine B business tells you that? So this is a surface of revolution. And what we've got is that, say that the radius, or the X, is equal to Z. So think about the line X equals Z. Rotate it, revolve it around the axis, and we get ourselves a sphere, or sorry, a cone. All right, so this is a cone. And then the V's being from 0 to 2 pi mean we're sweeping out the entirety of the cone. If it had only been, say, 0 to pi or something like that, it would only been half of it, but that's our full code. All right, so let's see if we can get this guy. All right, so we need to do RU and RV, and we need to cross them. So for this example, RU is going to be cosine V sine V1. RV is going to be minus U sine V, U cosine V, 0. So let's go ahead and cross them. So we're going to get minus U cosine V. For the y's, I'm going to get minus U sine V. And for the x, I'm actually going to get U, or sorry, for the z, I'm going to get U. When you do the z component, you're going to get a U cosine squared plus U sine squared, which when we pull the trick with sine squared, cosine squared just gives us U. So the magnitude of this is the square root of U squared cosine squared V plus U squared sine squared V plus U squared. Which is the square root of 2U squared, or U root 2. So because of the trig, this ended up simplifying down pretty nicely. All right, so now let's set up our double integral. So we're going to do the double integral of U root 2. In terms of du or dv, doesn't really matter. So I'll do du dv. The u's go from 0 to 4. The v's go from 0 to 2 pi. Which I think gives us 16 root 2 pi. But definitely please check my numbers on that. All right, so this is about as simple of a surface integral as you're going to get. And I just realized that I just said that, and some of you probably went, oh shit, this one's simple? Because, I mean, there was a lot to do here, right? But yeah, this was simple, because all we had to do was find the Jacobian. Otherwise, we have to not only find the Jacobian, but we also have to plug it into the function and then do all our things. So the fact that this is maybe the simplest of surface integrals makes you realize that surface integrals are not going to be a walk in the park. I mean, procedurally, they're the same thing every time, but what you're left with as your integrals can be kind of gnarly. This one just ended up being really nice, how everything played out. But that shouldn't surprise you. I mean, you think about it, we're finding the magnitude of RU cross RV. Magnitudes of vectors already are kind of gross because they've got roots. And then depending upon how U and V, you know, how those parameters play out, those partials can get rough. Now we're finding a cross product of it, right? So these things can be difficult. I just want to get that out in the open. But don't expect these to necessarily just be a really quick thing. But at least it's the same process every time. All right, so there you go. There's the surface area of this cone. And when I'm talking about surface area of the cone, I'm talking about the side, not the top, because the top doesn't actually exist. There is no surface there. All right, so now all of a sudden we have a tool for finding surface areas. So if you ever wanted to have a formula for surface area of a sphere, we can now, or of a cone, we can actually find it. What we would want to do is generalize this cone so that we're going up a certain h for our radius. That would change our parameterization a little bit. This guy wouldn't necessarily be u, but it would be some linear factor of u. This one ends up being just plain old u because the r and the h are equal. Obviously, if the r and the h aren't equal, that would change a little bit. But you go through the same kind of process and get a formula for surface area of a sphere, or of a cylinder. God damn it, of a cone. Whatever, sphere, cylinder, cone, all same thing, right? All right, well, I think I've now said surface area of a sphere probably 4 or 5 times. So let's do it. Let's actually find the formula for the surface area of a sphere. And we'll go generic. We'll go absolutely generic, which is the radius of r. So we get our surface area in terms of r. But before I go there, questions on this guy? All right, so you may know the formula for the surface area of a sphere. I don't know. Do you? Does anybody know it?
4 pi r cubed? No, it's not cubed. It's squared.
Yeah, you're very close. So it's 4 pi r squared. Right? You may have proven that back in, first year calc when you're doing integral stuff, right? When we show you integrals and using surface areas. Well, let me just go ahead and show you how a surface integral built, or how it gets built from a surface integral. So first of all, let's go with a sphere of radius big R. All right, so here's our parameterization then. We're going to use spherical coordinates. So we're going to have R cosine of u sine of v, R sine of u sine of v, and R cosine of v. So basically, I just made all the u's, or all the thetas u's, all the phi's v. And then R it's a fixed number, but it's the radius of that thing. And in terms of the restrictions on u and v, u is going to be between 0 and 2 pi, because that was our theta. And then what are the bounds on v? What were the bounds on phi for a sphere? Good. Jesus just put it. Oh, actually, it's not quite. It's not 0 to pi over 2. There you go, Victor Kata. It's 0 to pi. If we did to pi over 2, that just gets us the top half of the sphere. But we need to go all the way down just to pi. So, but it's only 0 to pi. All right, well, let's do this thing. Let's get RU and RV and let's cross them. So RU minus R sine U sine V. Then we get R cosine U sine V. And then 0. For RV, we get R cosine U cosine V. r sine u sine v, and then minus r sine v. All right, so now let's get RU cross RV. So it's going to be minus r squared cosine u sine squared v. That's the x component of it. The y component, we're going to get r squared sine u sine squared v. And
Real
then,
quick,
yeah.
shouldn't RV, the y component, be r sine u cosine v?
Yes, it should. Thank you. Which then changes this guy. Thank you for catching that this early on. That just saved us a lot of heartache. Actually, you know what? That doesn't change this one. Shit. Hold on. So, is that that guy's actually not part of that at all? Did that change the first one? No. Okay. This is still sine u sine squared v. Okay. All right, but it does change this next piece. So we're going to get a minus r squared sine u squared, so sine squared u, sine v cosine v. And then we're going to have minus another r squared, but now we're going to get cosine squared u sine v cosine v. Okay, I think we're good. I hope we're good. Now, before we actually get the magnitude of this, I want to simplify this last term. Because we can. I can factor out the minus r squared sine v cosine v from each piece, which leaves me another sine squared plus cosine squared, which goes away. All right, so we're here. All right, now let's get the magnitude. So that's going to be the square root of r to the fourth cosine squared u sine to the fourth v plus r to the fourth sine squared u sine to the fourth v plus r squared sine squared v cosine squared v. Oh, r to the fourth. All right, so now let's have some fun. Let's simplify. First, r to the fourth, I can pull out. That's just r squared. These first two terms, let me pull out a sine to the fourth v. So we get cosine squared u plus sine squared u. And And then this other part, we still have a sine squared v, cosine squared v. Well, this guy, of course, is equal to 1. Now, these both have a sine squared v. So I can factor that out. So I've got an r squared sine v, which leaves behind a sine squared v and a cosine squared v. Well, that, of course, is also 1. Its square root is 1. So what we're left with is r squared sine v. Whew. That's a lot of work there. So our surface area, I'm going to rewrite it over here. It's going to be the double integral of r squared sine v. And it doesn't matter if we do du dv or dv du, so I'll do du dv first. The u's go from 0 to 2 pi, and the v's go from 0 to pi. All right, so all of this work, all this stuff in purple, got us to the place where we now have our integral, our double integral, that we can use to solve for the surface area of the sphere. All right, so let's get that real quick. In terms of the u's, well, there are no u's to integrate, so we just get a u, which then when we plug in 2 pi and 0 gives us 2 pi. So we now have 2 pi r squared times the integral from 0 to pi of sine of v. Well, sine of v gives us a minus cosine of v to evaluate at pi and 0, which actually gives us another 2. And there you go. There is the surface area of a sphere. It's 4 pi r squared. So yet another way to prove the surface area of the sphere. Okay, are you ready to be mad at me? It's not gonna be, you're not gonna be mad at me, but you're gonna, yeah, you're gonna be mad at me. Matt, you're maybe ready. Okay, let me just draw your attention. So it's actually 4 times the area of the circle, right? The area of the circle is just plain old pi r squared. It's 4 times that, which is coincidental, but that's not why you're going to be mad at me. I just want you to look at something at the very bottom of the board. R squared sine v. So that ended up being the Jacobian, right? I mean, it's the little chunk that we need to convert to surface area here. You recognize that? Think Jacobians. Specifically, spherical.
Isn't that the Jacobian for spherical?
So remember, the Jacobian for spherical was rho squared sine phi. Well, the rho was the radius. Okay, well, now it's big R. And phi, well, we use the letter V as in Victor for that one instead. So because we had used spherical as our original transformation, we didn't have to go through all this work to find the Jacobian because we already know the Jacobian. Just like if we were doing this in cylindrical, what's the Jacobian going to be?
Wasn't that one just R?
R.
Yeah, it's just going to be R. Whatever the R happens to be, that's going to be its Jacobian. So you can be mad at me if you want. But of course, I do these things on purpose to show you that you actually already do a lot of this. Wait, I never mentioned it. Lord knows I never mentioned it back then. It's like, oh, well, check it out. This is going to be the area of the parallelograms that make the surface areas of the. No, of course I didn't. But they're all tied together. These things are all related because they're all Jacobians. We're just doing transformations. We're doing transformation, like when you parameterize a surface, you're doing a transformation. Because you're doing a transformation, you need a Jacobian. If that transformation is one we've already used, or we've already seen, like this spherical transformation we've seen, we've done lots of times. It's still a spherical transformation here. We should still get the same Jacobians because it's the same transformation. So this stuff all gets tied together, right? Like we learn them as individual little chunks, but they're all the same thing, right? Even stuff you learned back in integral calculus, your start is like when I mentioned the U sub and how you ended up having to multiply by something. Well, that was the Jacobian. Never thought about it that way, but it was. And so when we did the line integrals, and all of a sudden we're going from, S's to T's, yeah, we need that Jacobian. It's the same idea. Anyway, so be mad at me or not, just realize that if you can spot it, use the fact that you already know these transformations to keep you from having to reinvent the wheel. Because we actually went through this derivation. If you go back and you look at your notes, it either happened when we did Jacobians, or it happened when we did when we talked about the spherical coordinate system, or possibly both times. I don't really know. This could be the third time in this class that we've done this exact same derivation. It just felt like it was completely new because we're now doing surface integrals. Anyway.
Also, what exactly is R? I'm sorry, I was gone for like 5 minutes because
it's the radius of the sphere.
Oh,
it's the generic sphere radius. So it's a number. It's not unlike when we did integrals before with the rho and we allowed rho to vary. This one, it's a specific rho value. We're looking at only the sphere. All right. Okay, so for our surface areas, you just integrate one. For other integrals, well, we're going to integrate other functions. And so the question is, what are these going to do for us? Well, they're going to do anything that any integral does. You're going to add up those values. So suppose we have a surface of variable mass, or maybe not even variable mass, right? But if we've got a function that gives us a density per area, you integrate that density function over the surface area and you have a total mass of the object. I hinted at if we're looking at like charge, let's say that it's some sort of like a, a metal surface or something. We want to know the total charge on it. If you have a function that describes charge per location, integrate that over the area, or insert favorite thing here. Anything you're trying to add up over that surface, we can do it. Here's an example. Remember we were talking about the probability of an electron being somewhere, and we kind of got off on the tangent of Schrodinger's equation, Schrodinger's cat, and all that good stuff, right? The non-zero probability that one of the electrons in your finger is actually on Mars right now or whatever. Okay, so probabilities, if we now wanted to extend our idea of probability onto a two-dimensional surface, we would do set up an integral over that surface such that the integral over the entire surface equals 1. The integral over some region on that is the probability that you're located on that portion of it, right? So again, the uses are endless. They're literally endless. And so we'll definitely look at more examples as we go along of the different things we can do with them. We're also going to look at things like flux integrals. If we've got a surface and we want to talk about flow through the surface, okay, let's do a flux integral and all that. So we're going to keep talking surface integrals. I'm going to stop for today because I think I'm actually in the under 10-minute mark, and so I don't want to really go into too much more. So here's what our plan is going to be. On Wednesday, well, first of all, homeworks. There are homeworks due tonight, a couple of sections. Don't forget to get in there and work on them, due by midnight. Second, we are going to have an exam on Friday. And that exam is going to cover up to, let me look at my book here real quick. See how far I want to take it. Yeah, it's going to go through divergence and curl. So it's going to be 6.1 through 6.5. So it pretty much is just picking up where the last exam left off, right? The last exam was chapter 5 stuff. So this is going to be chapter 6. So what is this? Well, this is all this line integral stuff. So, vector fields, line integrals. So Green's theorem, conservative, non-conservative, curl, divergence, right? All that good stuff. We'll talk more about this on Wednesday. Okay, but we've got an exam 6.1 through 6.5 on Friday. So if you want to start getting prepared, go for it. So on Wednesday, my plan is to do a little bit more, talk a little bit more about surface integrals. Okay, show you some more examples, talk about things like flux and all that. And then we'll spend time reviewing for the exam. So we'll go over a little more detail what all these different things are, what I'm expecting out of you and all that. So that's the plan for Wednesday. And then, like I said, Friday, we've got exam 3. All right. Okay, so with that, any last questions before I stop the recording?
Are we going to have a final?
I believe so. It's on the syllabus, right?
Yeah, it's on there, but I mean, it's change. Things change.
As of right now, we are still set to have a final exam. Yep.
Is the final cumulative?
The final will be cumulative. Yep. All right. Well, then I'm going to go ahead and hit pause or stop on our recording, and I'll see you all Wednesday.